ARM Cortex M4 architecture is focused much now. All the Cortex M4, M1, M2, M3, M4 processors are a 32-bit reduced instruction set computing processors. Reduced instruction set computing processors means when we take 8051, it is a complex instruction set computing processor core, meaning it is having around 250 instructions, but in a reduced instruction set computing, all the instructions are less than 100. All the ARM Cortex M series of microcontrollers based processors are 32-bit in nature. Hence, the register length is also 32-bit. Here, this is the screenshot of ARM7 LPC2148 microcontroller. All the registers, if you see in the left-hand side, registers, there are registers R0, R1, R2, R3, R4 up to R15. Register 15 is called as program counters. Here you can see it is the program counter which is R15, it is pointing 23C. And able to see the pointer is pointing 23C. Look at the screen, look at the cursor. So the yellow color mark is the program counter. So it is pointing 0x00000023C. So this is a 32-bit addressing, right? So earlier in our memory window, this is a memory window of ARM processor core. Here if you see, the address is also 32-bit, register length is also 32-bit, and it is pointing the address 23C. This 23C is available in R15, which is treated as program counter. Oh, in all ARM processors, there is no separate program counter. The register 15 of all the ARM processors are used as a program counter. From this simulation window, it is clearly justified. And all the registers are of 32-bit. ARM is a 32-bit processor where the registers of ARM are 32-bit registers, and the memory size of the ARM processor is 32-bit. Hence, it can address 4 GB memory space. Even though it is a registers are of 32-bit, memory is of 32-bit memory, and the byte is also 32-bit registers, and the address is given to the individual bytes. Bytes are addressable even though there is a 32-bit register, even though the memory is a 32-bit memory, but each 32-bit memory has 4 bytes. Those 4 bytes have individual memory location. So ARM processor is having the byte address. Register length is 32-bit. So each register will have 4 address. Why? Because there are 4 bytes in a 32-bit register. So always, whenever you talk about ARM, memory, always the memory should be 0480, 0480, 0480, 0480. Program counter will always point from jump from 0 to 4, 4 to 8, 8 to C, C to 0, 0 to 4, 8, 0 to 8. 4 spaces it will jump. Why? Because every instruction is a 32-bit instruction. And 8-bit bus interface and all is clear, right? In addition to 32-bit data, the Cortex ARM processors can also handle 8-bit and 16-bit data efficiently. Say, for example, unsigned character. So, for D equal to 22, E equal to 44, F equal to 66, the bottom right corner, it is highlighted that in the Cth location, or the D, in the 22, 44, 66, D, E, F, all the variables are occupying some space in the data memory in in the 4000 something the data memory location. So 22 ஒரு byte எடுத்திருக்குது, 44 ஒரு byte எடுத்திருக்குது, 66 ஒரு byte எடுத்திருக்குது. Character variable occupies 1 byte space. In the ARM memory space, it is occupying byte. So it looks like 22, 44 and 66 in the same line, but the 3 memory locations. That's why this justifies the second bullet point. In addition to 32-bit data, Cortex M processors can also handle 8-bit and 16-bit data efficiently. This example is to justify ARM Cortex M processor is handling 8-bit data efficiently. And similarly, unsigned long integer means how many bit? In the 4000 is the memory location for variable A, where you can see 2 is available there. 4004 is the memory location for the variable B. So 4004 we are able to see 4. 4008 is the memory location for the variable C. So in the 8th location you are able to see 6. So from this, very clearly it is understandable So 32-bit data can be stored efficiently like this, and the 8-bit data can also be stored efficiently like this. Okay, through this example, we can very well justify that. In addition to 32-bit data, Cortex-M process can also handle 8-bit and 16-bit data efficiently. There is a need to discuss about ARM memory organization. Let us look at ARM memory organization. This is ARM 7 program memory space, whereas we discussed 00 to FF, sorry, 00 to FFFF. So in the right hand side, right bottom corner, we are having 0000. In the right top corner, you're able to see FFFF. The entire addressable space is here, which is a 4 GB space. This is ARM 7 LPC2148 based microcontrollers memory structure, where the program memory is a 512 kilobytes, right? Program memory is a 512 kilobytes. That means the program starts from 0000 to 7FFFF. Here you can see 7FFFF is 512 kilobytes. Okay, and your data memory is from 40000000 to 4007FFF is our data memory. And this is ARM 7 memory structure, and to justify that, right? To justify that, in the window you are able to see, right? The variables are occupying the space some 4000 something, right? Variables are occupying the 4000. Now, to justify that, here you see data memory space starts from 4000. So data memory space starts from 4000 because we are creating the variable. So variables are occupying some space in the data memory. So this data memory window in our Kyle IDE shows that it is 4000. So all the variables are occupying the data memory space in the memory structure. The starting location of the data memory itself is 4000, not 0. That is the moral of the story. Why? Because of von Neumann architecture. Okay, so user variables occupies data memory space in the memory map as shown. And the Cortex M4 memory structure is also similar to that. Anyway, that is also 32-bit. So memory system of ARM Cortex M processors uses 32-bit addressing, which allows the maximum 4 GB address space. Just like any other ARM processor, Cortex M processor also based on load store architecture. Load store architecture and this means data need to be loaded from the memory, processed, and then returned back to the memory using number of separate instructions.